Hello, I hope all of you are doing fine. Now, in the last session, we have a discussion on vibrations. So, we have understood what is actually vibration. So, we have understood that vibration is basically due to the residual unbalanced forces which are there in the system, due to which a system leaves its place from the equilibrium position, and it of course when it is the equilibrium position, so the body has a tendency to come back to its equilibrium position. So this fluctuating oscillatory motion, we have termed it as vibration. As well, we have understood the basic elements of vibrations, where in inertia we have seen inertia, then restoration and dissipation. These are the three basic elements of vibration which must be there in the system. So even then we have tried to classify them like free vibration, forced vibration, damped, undamped, single degree, multi-degree, and so on, longitudinal, transverse, angular, torsional. So we have classified them in whichever way possible we can classify them. Now comes the question of analysis of such vibratory system, how we are going to analyze this. So when we are doing the analysis, as we are saying that if we understand vibration, then only we will be in a position to control this, or we will be in a position to utilize this. So we need to do this analysis. So we will start up with one of the most basic or the simplest system, which we will take up as free vibration. Of course, without damping, I am saying free vibration of single degree of freedom system. So we'll try to understand this free vibration of a single degree of freedom system. By single degree of freedom system, we mean that only one variable is in a position to express the entire equation of motion of that system, right? So now, before we get into the actually into the single degree of analysis part of it, let us try to again have a look at the types of what you can say, types of systems. So we can broadly classify this type of systems into elastic, you can say elastic restoration. As we know, restoration is one of the basic elements of a, and second we can call it as a field restoration. So in elastic restoration, again we can categorize this into two parts. By elastic restoration, we mean the material property, due to the material property of involved in that system. So the elasticity or the rigidity of that, or the stiffness for that matter, of that system, which is going to influence the equation of motion. So in this, of course, linear and like can say linear motion and angular motion, right? And by field restoration, we mean can be when the field is affecting into the equation of motion. So it is restoration is due to gravity, or it can be some other influencing medium, can be magnetic or electric field or something like that. So we will not be getting much deeper into this right now. So again, in gravity we can have system as again linear motion and angular motion of the system. So in linear motion we can see this example, like there is a cantilever beam having some length and there is a concentrated mass at the end. So the motion is linear, but it is perpendicular to the longitudinal axis. So we will put this into longitudinal transverse vibration. We can have a system maybe like this. Now of course we are taking this system as an undamped system, so that is why I am not showing any kind of damper in this system. So maybe natural damping we can consider. And then in angular can be a disc so which is getting twisted about the axis. So here it is mass and the displacement is linear, and here if I say this will be the mass moment of inertia of the system and the displacement is angular, so as theta. Now in gravity, in linear condition, example can be like displacement of say this kind of a system is there. So there is a fluid, so by gravity when it is displaced, so there is a vibration in this mass of the liquid. So this we can say as the linear displacement, which is due to gravity. Then in angular, one of the simplest example can say a pendulum with angular displacement theta. So this is again an angular displacement. Another example can be a cylinder which is on a rough surface or horizontal surface, and when it is disturbed from the mean position, so it starts rocking. So this will be angular vibration will be there, which will be again due to gravity. So this is how we can say, we can differentiate this into various systems. So now we will move on with trying to do the analysis or get the equation of motion, in which the first approach is the Newtonian approach, Newtonian mechanics. We are calling this as Newton's method. So in Newton's method we know, or we can understand, that the force is mass, product of mass and the acceleration, and moment or torque can be represented for angular motion as mass moment of inertia into alpha. So these two equations are representing the Newtonian mechanics or Newton's theory. So on the basis of this we will try to or with this approach we will try to first get the equation of motion for a simple free vibration single degree of freedom system, right. So let us try to get the equation of motion by Newton's method. So the approach is of Newtonian mechanics. So let's take up an example where there is this mass m and so let us say it's a frictionless surface. So there is no friction as such here, so we are neglecting that part. So by lumping the characteristics or parameters, so we have lumped the mass parameter and this as the stiffness. So let us say it is having a stiffness of K. So say this is the mean position, so this is the equilibrium position. Now in case of vibration, the displacement will be always measured from the equilibrium position. So say at this instant this body is displaced, say in this direction x. Now as we know, when this body moves, say in this case to the right, so this due to this presence of spring, the spring will try to pull it back or bring it back to, or the stiffness or the elastic property of this material will try to pull back this mass to its equilibrium position. So if we see the free body diagram, so when say from here, say when it is moved in the x direction, so it is moved in this direction, so this spring is going to pull it back to its equilibrium position. Now if you want to work out with the forces which are there in the system, so forces will be acting horizontally and vertically, but if you see this situation, maybe the weight of this mass and the reaction from the surface, say let us say they are cancelling out each other, so there is no force in the vertical direction. But if we see in the horizontal direction, so in the horizontal direction, when this mass is getting displaced by x at time t, so displacement is x, so when it is getting displaced, so according to Newton's law we can say that the force exerted by this mass will be mass into the acceleration. So I can say this force F in the horizontal direction will be equal to mass into the acceleration. So this is what is that force, which is mass into acceleration, right? And the spring is pulling back the mass, so the force applied by, or force due to restoration force or the restoration, so this is the inertia, so restoration is the k into the displacement x, I can say, right? So the restoration is done by restoration force, so let us say F restoration is kx. Now you will see that the magnitude of this two must be same, but their senses are opposite, or they are acting in opposite direction. So I can say that kx is equal to minus ma, right, where a is the acceleration. So I can say that, so I'll bring it to the same side, so mass into x double dot x dot is velocity, x double dot is rate of change of velocity, will be x dot is velocity, x double dot will be acceleration, which is equal to 0. Or I can put this equation in the form as x dot k by m into x is equal to 0, and then I can compare this equation with the equation in the form x double dot omega n square x is equal to 0. So I am getting this equation as this. Now why I am equating it into this? So if you see, this is the equation of a harmonic motion, or a simple harmonic motion, I can say, because now if you see, let us talk about this. If I take up this equation, x double dot plus omega n square x is equal to 0. So if you find out the solution for this equation, you will get that the solution of this equation will come out to be x of t will be equal to a sine omega n t plus b cos omega n t. So you see that we get this equation in the form of, or as a function of, sine and cosine, or sine or cos, so which is a harmonic equation, right? So this is a, so we can understand whatever this motion is, it is a harmonic equation. And the omega n here, what we are saying, this is the natural angular frequency of that system, because now we can have different situations for this equation as a solution, right? So if the equation is such, so I can plot a graph between the time and displacement. So if I plot a graph between time and displacement, so I can have three solutions, I can get three kinds of solutions. So first solution can be something like this, wherein we can say that this x is equal to x sine omega n t. So this is like b is coming out to be 0. So this equation means, so at x is 0, at x0 means it is the displacement. So at time t0, the displacement is 0. So that means at time, at the start, there is no displacement, but at time 0 there is some velocity. So that means during the start there is no displacement, but rather the system is actuated, or it starts with a velocity. So I can get a sine equation. Now in the similar way, the solution can be, say, when we again I place try to get a graph, so I can get an equation something like this. So if this is the equation, that means the equation is x cos omega n t. So that means, say, a is coming out to be 0. So I am getting this displaced equation to be as this. Here then I can say at x at time 0 it is having some displacement, but at time 0, at time t is equal to 0, the velocity is 0. So I am starting or the system is starting with a displacement. So there is a displacement, but the velocity is 0, and that is how the system is getting actuated. And third solution, possible solution, can be the combination of these two. So if I show that graph, so maybe it will be something like this. So this will be then as this equation. So anyway, if we see the solution of this equation, so we are getting the equation of motion of this system as a harmonic equation. So here this omega n is representing the natural frequency. So frequency by V mean, so it is the, so for this I can say this is the time period for one cycle. So the angular frequency, we can say omega n will be equal to under root of k by m, right? And this is in radians per second. Now this is one of the important parameters which we always try to determine. So every system is going to vibrate or have the frequency of vibration according to the parameters of properties of that system, like K is involved. So based on the restoration and the mass, so that is going to decide the natural frequency. So this is the angular rotational frequency, and in terms of cycles, if we say, though, this will be omega n upon 2 pi. So that means if we rotate a vector for 360 degrees, so we are getting this expression. So when we are rotating this vector, right, so omega n will be the number of cycles per second divided by the displacement. We will get this as in hertz. So we will get, or the natural frequency is 1 upon 2 pi under root of k by m. In terms of cycles per second we will get, so cycles per unit time, that is in hertz, right? So this is what we are trying to find out. So that is what we have seen in this type of system. So when we are approaching with Newton's method, so we get the equation for the natural frequency as this. Now if we change the system, now in this case, if you see, there is no role of gravity as such. Let us try to understand a system wherein there is a gravity, but the restoration is not due to gravity, right? So the system is subjected to gravity, but so if we take up this second example, let us say, right, having some stiffness K. Fine. Now what happens in this case is, when it is a free spring, now the moment I put a mass, or moment I hang a mass on this spring, what is going to happen is, this mass is going to move, or the spring is going to get stretched a little bit to reach an equilibrium position. So maybe I'll show it as maybe somewhere here. So that means the mass is getting displaced from here to here. So I will name this as delta, or this as the static equilibrium position, or static deflection I can say. So this is the static deflection, right? So what is the static equilibrium condition. Static equilibrium condition is this mass under the influence of gravity is, now here spring will be giving it a opposing force, so this will be equal to K into delta, where delta is the static deflection. So maybe I can say this as mg minus K delta is equal to 0. So say this is equation 1 for me, right? And now from this equilibrium point onwards, so I have said earlier that the displacement is measured from the equilibrium position. So let us say this is moving in this direction, x is moving in this direction, so there is displacement. So the system is right now vibrating in this fashion. So now what we can say here is the total force in the system will be same or will cancel out each other. So when the body is moving with a displacement x at time t, so I can say this is the total force on the system when the body is moving will be equal to the total force, that means the self weight mg, which is acting downwards. Mg is acting downwards, right? The restoration K into delta. Now here when this is happening, x is in this direction, so K already there was delta and displacement x, so K into delta x, this force, and you can say when it is moving in this direction, this is the force by which it is moving. So this I can say will be equal to mg minus K into delta plus x, or we can say mg minus K delta minus Kx, and from this equation we can say this is equal to 0. So I can say m double dot plus Kx is 0. So again we are reaching to the condition or the equation of motion to be as this for a single degree of freedom system, so which is having an analogy with the equation of a harmonic motion, x is equal to 0. So here we can say the natural frequency, where this is the angular frequency, will be under root of K by m radians per second, and the natural frequency in terms of cycles per second we can say this as under root of K by m hertz. So again we reach to this situation, right? So that is how we can say, or we reach to this condition. Now these are the linear systems. Now if you see an angular system, say if there is this system which is rotating by theta, say this is having a mass moment of inertia I, so we can reach to this equation. So it will be I theta double dot square, where it is having, say, Q as the angular stiffness, into Q theta to be 0, where we can say theta double dot plus Q upon I theta is 0. So the natural frequency, again we can say under root of Q by I as radians per second, or natural frequency to be 1 upon 2 pi. So it will have analogy to angular equation of harmonic motion, or the equation of motion will be the harmonic equation. So this is one of the methods called as the Newton's method, with the help of which we are in a position to determine the equation of motion. So this is the equation of motion, we are calling this as the equation of motion, with the help of which then we can determine the natural frequency of the given system, where this is a free vibration without damping. Now there is another method which is called as the energy method. Let us see that method as well. So let us talk about another method, with the help of which again we determine the natural frequency of vibrating system. This is called as the energy method. Now, if you remember during the classification, when we have talked about damped vibration and undamped vibration. Now, in case of undamped vibration, it is assumed that the dissipation component is quite negligible in a way. It is existing, but it is quite negligible. That means the energy is getting conserved in the system, right? Whereas in case of a damped vibration, so the energy is dissipated with the help of some medium, with the help of a damper. So the life of the vibration, you can say, is lesser compared to free vibration. So when we are talking about a free vibration, so that means we are talking about the conservation of energy. That means what? It means that the total energy of the system, the total energy of the system is remaining constant, right? That means the form of the energy is changing, but the total energy in the system is remaining constant. So this total energy, we can say, of the system will be the kinetic energy and the potential energy. Now the kinetic energy is, you can say, it is due to the motion of the body, the displacement of the body. And so again, let us say, if I take up this the same example as this, so having mass with some stiffness as k, and this is the equilibrium position, and the displacement is taking place this way. So when this is moving, so kinetic energy. And what can be the potential energy? The potential energy can be, again, this can be in the form of gravity or gravitational energy, you can say, or the strain energy, right? The strain energy of the system. So if it is a spring, so it is the strain energy which is there in the system. So that is how we can say that the total energy, that is kinetic energy and the potential energy, sum of these two, neglecting other whatever energies are there, these two to be constant, right? So when this is constant, that means I can say by dt will be 0, right? Or I can say d by dt of kinetic energy plus the potential energy as it is constant will be 0, right? Now if you see this system, for this system the kinetic energy will be equal to half mv square, right? Or when the motion this is linear, so I can say that this is equal to half m, x is the displacement, so x dot is the velocity, x dot square will be the kinetic energy. Now what about the potential energy? The potential energy is in the form of strain energy. So this will be equal to, if you remember, if we express for a spring, say for a spring it is having K as the stiffness and it is subjected to say some force, if we say, and if we plot the graph between the displacement or expansion of the spring, that is x with F, we get this as a straight line, where this line will be definitely, slope will be kx, right? And for a value of x, the area under of this curve will be the work done, right? So area under this curve, if I say, then it will be x into F, and where F is equal to kx, right? So if that is the case, so area under the work done, so that means we can say half base into height, that will be the rate of work done, which will be the potential energy. So this potential energy will be half kx square. Fine. So we get the potential energy expression to be as this, kinetic energy expression to be as this. So now we can say d of this will be d by dt of half m x dot square plus half k x square, and this to be as 0. So if we differentiate this equation, so it will be half m twice of x dot x double dot. So this is partial differentiation we are doing, half k twice of x and x dot. So this will be equal to 0. So in this equation we see x dot can be cancelled out from this equation, right? So I can say m x double dot plus kx is equal to 0. So again we have reached to the situation k by m into x to be 0, again which is in the form of the harmonic equation, has an analogy with the harmonic equation. So again, for a single degree of freedom system with free undamped vibration, again we reach to the same expression, we get omega n to be as under root of k by m radians per second, or the natural frequency is 1/2 pi under root of k by m hertz. So this is how again we can apply this energy method to again get the equation of motion for the given system, and we can determine the natural frequency of the system. So given the system, then we can understand this, and we now know these two approaches. So with the help of these two approaches, then we are in a position to analyze and get the equation of motion, and hence we can determine the natural frequencies of the system. So that's all in this session.